Hello and welcome to our first asynchronous session. Today we're going to concentrate on writing and solving equations. Before we can do that, we need a little introduction to variables. So let's start off with some vocabulary. A variable is a symbol used to represent a number that is either unknown or can change. Alright, so examples of variables are, as you've seen, any letter, X, Y, Z. I could have a question mark, I could have a blank, I could have a box. It's just any symbol. It doesn't have to be a letter. Anything that's taking the place of something that we don't know. On the other hand, a constant is a number that doesn't change. In math, we call that something that is static. Alright, so examples of constants are just the numbers like 3, 5, -4, a third, square root of 2, 4.56, just anything that's a number that doesn't depend on a variable like X or Y or Z. So what do we use variables for? What are they good for? Well, we use the variables in math to write equations where there's an input. So like we ask for a number and the input is called the variable. Alright, then we do some math to it and then we get an output or an answer. So in other words, we use variables so that we can tell someone what steps to do to solve a problem instead of just giving an answer to one individual problem. So consider the example. I have a single situation where variables are not required like the one on the left. So a bus pass in Phoenix for minors costs $2. How much does it cost for 8 bus passes? This represents the typical question that you've been used to dealing with up to this point in your math careers. We know that each bus ticket is $2 and there are 8 of them, so all we need to do is 2 times 8 equals $16. No variables needed. But let's restate that same problem so that we have to write an equation. Alright, so an example is, here's our same example. A bus pass in Phoenix for minors costs $2. Write an equation to figure out how much it would cost for any number of bus passes. See, this is more powerful because I'm telling an individual what you have to do to get the answer if you tell me how many bus passes you want. Not just the single example of 8, but for any number. So on the left here we can see that, well, I took the number of bus passes and I just multiplied it by 2. So to get the total number of dollars, we're going to take 2 times the number of tickets that we need, because each ticket costs $2. And then I just simplified that down on the bottom to say D equals 2 multiplied by X. And remember, X is our number of tickets. So if I wanted to figure out again how much 8 bus tickets cost, I would just plug in 8 for the X, and it's 2 times 8, just like we did on the left. But then I could plug in any number for X that I want. I could figure out how much it costs for 20 bus passes, which would be 2 times 20, or 40. Alright, so let's practice identifying the variable in these equations. Alright, so I have 5 times z equals 10. Clearly z is the variable. 5x equals 10. And when I write 5 and then an x equals 10, it does mean 5 multiplied by some number equals 10. Just like this statement is the exact same statement as the one above. 5 and then I have the multiplication symbol question mark. So 5 times some number equals 10. Just like what was stated above. They mean the exact same thing. Where the question mark is the variable. And then finally in this last equation, the variable is m. Alright? How about in this example? Movie tickets cost $8 each. The total cost of buying any number of movie tickets is modeled by the equation below. C equals 8x. So think about how we would figure out the total cost of buying X number of movie tickets. Alright, so since they're $8 each, I would just take the number of tickets that I need to buy and multiply it by 8. And that's exactly what this expression is telling me down here. So C, in this case, probably means cost. Alright, it was equal to 8 times the number of tickets you bought. So here, the variable, of course, is The number of tickets. That's what can change. The price doesn't change. The price is always $8 a ticket. It's the number of tickets we buy that can be a variable that can change. So here we decided to use x again to represent that. And usually in equations we use x, but it can be any symbol again, any letter. So let's go on and talk about what an equation is. All right, an equation is a mathematical sentence with two expressions set equal to each other. So down below I have an example of an equation. And to be an equation, all you have to do is look for the equal sign. That's what makes it an equation. So pretty much anything you see that has an equal sign in it, we call an equation. If it doesn't have an equal sign in it, if it's just something like 3x plus 5, we would call that an expression. So to be an equation, it has to have an equal sign. Otherwise, we call it an expression. So equations can be solved for their variable, right? To solve an equation, it is important that we isolate the variable. In other words, we try to get the variable all by itself. And in this case, the variable is x. So how do we do that? Well, we do that with what we call inverse operations. So I want you to think of an equation like being a balance scale. Okay, and whatever you do to one side of the equation, you have to do to the other. You can do absolutely anything you want. You can add whatever number you want. You can multiply by whatever number you want. Divide, take the square root, square. As long as you do it to both sides, you're going to get a true statement. You're going to keep that balance equal. So if I add something to the left-hand side, I got to add it to the right-hand side, or else I don't make the expressions equal to each other anymore. And then I've changed the equation. So some rules to remember when you're trying to solve for an equation. The ones that you're going to see most is that addition and subtraction are inverses of each other. That means they're the opposite. So they undo each other. And the other one that we're going to work with is multiplication and division. They undo each other. They're opposite. So for example, if I take a number and multiply it by 2, and I want to undo that, well then I just divide by 2. So again, in summary, addition and subtraction we call inverse operations. So you'll hear that word inverse used a lot in math, and it always means the opposite, or to undo something. And multiplication, and division are inverse operations. They also undo each other. So let's do an example using a one-step equation. All right? We call them one-step equations because literally they only have one step to get the answer. So consider this equation. 4x equals 12. Now what does this mean? We know that this means 4 times some unknown number, so multiplied. Remember, when I don't need to write the multiplication sign in between. When I write them right next to each other in math, that means multiply. So this says 4 multiplied by some number equals 12. Now, if you're familiar with your multiplication table, you don't need to do any fancy algebra to solve this equation, right? You say 4 times what number is 12? And most of you probably in your head can come up with the answer of 3, because yes, 4 times 3 is 12. But let's get used to solving it using inverse operations. You'll want to do that because when the equations become more complicated, when you can't just do them in your head, you need to know how to undo things, how to move things to the other side of the equation so that you isolate the variable to get the x all by itself. And in this case it says all by itself on the right side. I think we meant to say the left side. But in reality, it does not matter what side the variable is on as long as it's by itself. Because again, saying x equals 5 is the same thing as saying 5 is equal to x. So here's the variable that we're trying to isolate, trying to get by itself on the left-hand side of the equation here. So we need to move that 4 away from the x. So how do we do it? Well, as we already discussed, since 4x does mean 4 multiplied by x, we need to undo multiplication by doing the opposite of multiplying, which is division. So we need to divide both sides of this equation by 4. So when I write the bar here and I'm putting a 4 under here, I'm not bringing a 4 down. I am doing an operation. The operation I am doing is dividing the left-hand side of the equation by 4. That's what that division sign means, right? And then, like we discussed earlier, if I divide the left-hand side of the equation by 4, I have to do it to the right-hand side of the equation to keep it balanced. So in this case, 4 divided by 4 is 1, or they cancel out, because 1 times x is just x. So now this is how we've isolated the x. We've gotten the x all by itself on the left-hand side, and that we get our answer of 3 because 12 divided by 4 is 3. And we already knew that, right? We knew that 4 times some number equals 12. That number was 3. But when solving an equation, it's always a good idea to go back and check your work. And this is easy to do. So suppose we came up with the answer 3. And we're looking at our original equation of 4x equals 12. To check my answer, I just plug my answer I got back in for x into the original equation. We call that substituting. So in this case, I replace the x with 3, our answer. So 4 times 3 equals 12. So 4 times 3 is 12, and then we get that 12 is equal to 12. That's a true statement, so the answer worked. So we know that 3 is indeed correct. How about we try one with a fraction? So we have 2/3 times x equals 7. So how are we going to undo multiplying by a fraction? Well, we want to get the x all alone. All right? And because 2/3 is a fraction, we're going to have to multiply by the reciprocal of that fraction, the flip of it. Notice 2/3, the reciprocal of 2/3 is 3/2, or 3 over 2. Then we multiply that by both sides of the equation. Well, why do we do that? Well, if you recall from learning how to divide fractions, right, this does mean, in fact, 2/3 times a number. Well, how do I undo times? We already said we undo that by dividing. So technically, I'm dividing both sides by 2/3. But remember, when we divide a fraction by another fraction, we take the reciprocal of what we're dividing by and then multiply. All right, so in this case, let's just go ahead and multiply both sides by the reciprocal right off the bat to get the x all by itself. So here you can see where I'm multiplying the left-hand side by 3/2, and then I go ahead and I multiply the right-hand side by 3 over 2. On the left-hand side here, we get a bunch of canceling. Whenever I have a 2 on top and bottom, or the same number on top and bottom, they cancel out. But look, we also have a pair of 3's that we can do that with. They cancel out. So what are we left with? Just x on the left, like what we want. So now to get our answer, we have to multiply 7 times 3/2. The way that I do that is I'll rewrite 7, and let me show you with my pen here. I'm going to rewrite 7 as a fraction. Remember, any whole number can be written as a fraction over 1. And then I'm going to multiply that by 3/2. So recall from last year, when you are multiplying fractions, you do not need to get a common denominator. You just can multiply straight across. So 3 times 7 is 21, and 1 times 2 is 2. So a lot of times it's acceptable to leave your answer as an improper fraction, as I have done here. You might want to write this as a decimal. So if you divided that on your calculator, you'd get 10.5. You might want to rewrite it as a mixed number, and I'll show you how to write things as a mixed number in a couple of slides. Finally, we got the answer 21 over 2, or 10.5. We'd want to check to make sure that is indeed the correct answer. So let's say I took the number 10.5 and I plugged it in for x in our original equation, right? Then 2 times 10.5 divided by 3 should equal 7. And you can go ahead and check that on a calculator to verify that it indeed does equal 7. You could also work directly with the fraction. So let's do an example of a one-step equation. Alright, so this problem here contains subtraction. So take a moment and pause the video and think, what should we do to undo subtraction? How are we going to isolate y? How are we going to get that variable by itself? Right. If you said we undo subtraction with addition, you are correct, because addition is the inverse or opposite of subtraction. So I add 4 to the left-hand side, and then whatever I do to one hand side, I have to do to the other. Notice that a minus 4 and a plus 4 is 0. That's how we get y by itself. So y plus 0 is just y. So here the 4's, we can think about them as canceling out. Remember, they undid each other, leaving me just y on the left-hand side. So we get the answer that 12 plus 4 is 16. And then the last thing I would do is check in the original equation to make sure 16 worked. So I would take the 16 and go back to my original equation and replace the variable with it. So then I would, replacing y with 16, I would say, is 16 minus 4, does that really equal 12? And yes, 16 minus 4 is 12, so I know my answer is correct. How about we try another one? So this problem contains addition. So what do we need to do to undo it? If you said subtraction, you're correct. So since we are taking some number and adding 7 to it to equal 5, to figure out what that some number is that I added to 7 to get 5, why not just subtract 7 from both sides to figure out? Do the inverse, do the opposite. So on the left-hand side, I'm just going to get x, because the plus 7 and a minus 7 cancel out because they add up to 0. So we just get x on the left-hand side, and then you got to remember your rules for addition and subtraction of integers. 5 minus 7 is negative 2. Alright, so the rules when you're subtracting integers, right? I could rewrite 5 minus 7 as 5 plus a negative 7. And since the signs are opposite, I should subtract these numbers. Okay, well 7 minus 5 is 2. Then I keep the sign of the larger number. So this is negative 2. Another way to think about it is with a number line. Here's 0. And if I start out at 5, 1, 2, 3, 4, 5, and here I am with my dot, and I subtract 7, that means I have to move back to the left 7 times. Well, you can see that 1, 2, 3, 4, after 5 I'm already back at 0, but I still got to go back 2 more because I got to go to the left 7 times. So 5, 6, 7. So I am at the position negative 2 on the number line. So take a moment and solve the following equations. Alright, so let's consider the first equation. 7x equals 9. That means 7 multiplied by some number is 9. So how are we going to figure out what the x is? Whoops, let me go backwards. Alright, so in this case, I need to undo multiplication, because remember, when I write them right next to each other, we don't put the time symbol, but when they are right next to each other, it means to multiply. So anyway, I'm multiplying 7 times some number equals 9. So before I even undo and solve this equation, I'd like to kind of think about what kind of answer I'm expecting to get. So I know that 7 times 1 is 7, so it's a little too small. If I plug in a 2 where the x is, then 7 times 2 would be 14. That's not equal to 9. That's a little too big. So I know this is a decimal answer, it's like somewhere between 1 and 2. So if I somehow solved this problem and ended up with a number like 63 for an answer, like if you accidentally multiplied 7 and 9, you should understand that that doesn't seem right, because 7 times 63, there's no way that's equal to 9. Alright, so go back and check your work in that way as well. So in this case, we're going to go ahead and we're going to isolate x, we got to undo multiplication. So that means divide both sides by 7. When I put the bar here and I write a 7 under it, I'm not just making a picture, I'm performing an operation. I am indicating that I am dividing this entire left-hand side by 7. That way the 7's cancel out. And remember, what we do to the left-hand side of the equation, we must do to the right-hand side of the equation. So in this case, we get that x is equal to 9 over 7. So this problem is exactly the same, just with different numbers. 8 times x equals 64. So I want to undo multiply by 8. So just like in the last problem, to undo multiply by 8, I need to divide both sides by 8. So then we get that x is equal to 64 divided by 8 happens to be 8. So this is an example like the one that we had a few slides ago. 5/6 times some number is equal to 30. Alright? So remember, the shortcut for getting rid of multiplying by a fraction, right, is to multiply by its reciprocal. So in this case, I'm going to choose to multiply both sides of the equation by 6 over 5. See, I just flipped the fraction upside down no matter what it is. I just flip. I put the denominator in the numerator, and I put the numerator in the denominator. I switch them. That's called the reciprocal. But again, if this is what I did to this side, then I got to do the same thing to the right-hand side. So I multiply this side by 6 over 5. Now on the left-hand side, the 6 will cancel out with the 6, and the 5 will cancel out with the 5, and that leaves us only the x. That's what we're trying to isolate, get by itself. And now again over here, we are multiplying fractions. Notice how I just instinctively put 30 over 1, right? Because 30 divided by 1 is 30. So I didn't change the value of this number. I just wrote this whole number as a fraction so that it makes it easier for me to multiply, so I know what to multiply. So there's two ways you can do this. One is you can multiply straight across, all right? And we'll do that way first. We'll do the brute force method. So 30, without thinking, I can just go 30 times 6. Okay, so I'm just doing steps, and I would say that's 180. And then I'm going to divide 180 by 5. All right, and if I divide 180 by 5, all right, I'm going to get that 5 will go into 180. So 5 goes into 18 3 times. 30. And then 5 goes into 30 exactly 6 times. So 180 divided by 5 is 36. You could have also done that by doing cross-canceling. And that actually saves you time if you notice it. So when I'm factoring, I can simplify these fractions first and then multiply. So I notice that 5 will go into 5 one time, and 5 will go into 30 6 times. So I did some cross-canceling there, and then notice how we just have 1 on the bottom. And now if I multiply the tops, I get 6 times 6, which is 36. 1 times 1 is 1, so 36 over 1 is just 36. So we get the same answer. Do whatever way is most comfortable for you. The first way, you don't have to think about what goes into what. You can just multiply across and divide. The second way, if you don't have a calculator at your disposal, can save you a lot of time. But you have to be better at your factors, knowing your multiplication table. Alright, so this last example here, I have x divided by 4 equals 9. That's how I read that, right? That some number divided by 4 is equal to 9. So I got to try to get the x by itself. So in this case, the variable is being divided by 4. So immediately I'm thinking to myself, what should I do to undo that? What is the opposite of divide by 4? Alright, and recall that the opposite of division is multiplication. So if I'm taking a number and dividing it by 4, and I want to undo that, then I need to multiply it by 4. So I'm going to take x divided by 4. I'm going to go ahead and multiply that side by 4. And again, I wrote it as a fraction just to make things line up a little nicer for me. And if I multiply the left-hand side by 4, I have to multiply the right-hand side by 4. Now notice when we have the same number on top and bottom of a fraction, when they're being multiplied, I can cancel them out. So all we're left with on the left-hand side is our x, which was what we were trying to get. And the right-hand side simplifies to 9 times 4, which is simply 36. So does 36 reasonable? Does that answer seem right? If I'm not sure, I should take my answer, 36, and substitute it back into the original equation for the variable. Because here I'm saying that x is 36. So let's really see if it is. So if I replace this x right here with 36, does 36 divided by 4 equal 9? Yes, it does. So now we know we can be guaranteed that 36 is correct. So let's do an example of writing an equation. Jack needs a total of $40 to buy a new video game. Jack already has $10. How much money does Jack need in order to buy the game? We want to write and solve an equation and let x be the number of dollars needed. So whenever I'm writing an equation, when I'm working with these word problems and I'm going to write an equation and solve it, the first thing I have to do is identify the variable. I got to ask myself, what are we trying to figure out? You know, when you're reading a word problem, usually you can go right to where the question mark is and say, that's what I'm trying to figure out. That's what I need to make a variable for. But in this case, it was defined for us. It said, let x be the number of dollars needed. All right, so how much does he need to buy that game? Which is what the question is asking anyway. So I'm going to go ahead and write that. Well, we're going to call x, and I'm going to go ahead and write out that x is equal to the dollars needed. It's really important that we define our variables so that later when we're doing our math, we don't forget what the variable represents. Okay, so now let's go about writing our equation. So remember, writing the equation means, how do I figure out, how would I figure out how much money he needs? Let's say even if I wasn't using, in this case, writing an equation, if I were just to figure out how much more money Jack needed. Well, a lot of you might say, well, since he needs 40 and he already has 10, I can just do 40 minus 10, which is 30. And yes, that's true, but we can also think about it like this, that I have some unknown number of dollars, like we don't know, we need some number of dollars, and if I add that to the 10 I already have, then I have a total of $40 which I need to buy the game. So again, take some unknown number of dollars, I plus the $10 that I already have, and that equals the $40 total needed to buy the game. Right? Is that the only way we could have written the equation? No. You could have also gone ahead right off the bat and said that the number of dollars we need is equal to 40 minus 10, which gives you your $30, which we can tell the answer is 30, right? Because 30 plus 10 is 40. But let's go ahead and solve that using our inverse operation. So we're going to solve the one-step equation, x plus 10 equals 40. So what we need to do is subtract 10 from both sides to undo addition. So a plus 10 and a minus 10 cancel out. So on the left-hand side, we're just left with x, and 40 minus 10 is 30. So Jack needs $30 to buy the game. All right, so sometimes we can write more than one equation to solve a problem. So if you're asked in your lessons to identify which equation models this situation, go ahead and solve the equation out and see if you get the correct answer. Because in this case, it's pretty easy to see that the answer is he needs $30 more. So suppose I gave you a whole list of equations, and this might have been one of them, right? Like this is the correct answer on your workbook that you need to pick. But they also might have written like x minus 10 equals 40. So maybe it's that one. So you're thinking, well, maybe it's that one. Well, if you're not sure, go ahead and solve this equation. To solve this equation, I would add 10 to both sides. And then we'd get the answer of 50. And then go back and read the problem again. Does $50 make sense? Wait, he only needs a total of $40, so how could he need 50 more dollars? So then you would know, okay, this expression cannot be correct. So go ahead and think through those kind of problems in that way. You know, you can always check. Let's try another one. Okay, John needs to order shirts for his baseball team. Each shirt costs $10. First, we want to buy an equation to model the cost of buying X shirts. That means any number of shirts. And then we're going to go ahead and solve it for a specific situation. If there are 12 players and they each need a shirt, how much money does he need to buy the shirts? Alright, so our first step is to define the variables because we're trying to write this equation. Well, they already kind of told us that go ahead and use X. But what is X going to be in this case? What should X be? What is the unknown? What can change in this situation? The cost of the shirt doesn't change. The cost of the shirts are always $10. What changes is the number of shirts we buy or how many teammates we have on the team. So that's what the variable in this case should represent. X should represent the number of shirts we're going to buy. Then we're going to use that information to write an equation. Alright, so I'm going to say the cost is equal to 10 multiplied by the number of shirts. Because think about it, if I have 5 shirts and they each cost $10, then the total cost would be 10 times 5 or $50. But remember, I don't want to solve it for a specific example in this case when I'm writing the equation. I want to tell you what to do to figure out what the cost would be for buying any number of shirts. So I said the cost is equal to 10 times the number of shirts, and then I went ahead, instead of writing out the entire word cost, I just shorthand it. You know, I made it a letter C. Let me know that stands for cost. And then the number of shirts here is what we defined as the variable X. So here it's saying the total cost is equal to 10 times the number of shirts you buy. So if I want to figure out the cost of buying 12 shirts, as being asked in B, right, then all I need to do is replace the variable with the number 12 and solve. So that would mean replacing the X with 12, and then when they're written right next to each other like this, remember that means multiplication. So this does mean 10 times 12, and 10 times 12 is 120. So for 12 players, the cost would be $120. That concludes today's lesson. Make sure you click on the announcements where it says the Asynchronous Session 1 questions. Answer those questions and submit them to me. If you have any questions, please email me. Thank you.